আচ্ছা স্যার, আপনি কি রেকর্ডিং আর ছাড়েন না ইউটিউবে?
চ্যানেল দেখছো?
জি জি স্যার, দেখছি তো।
চ্যানেলের প্লেলিস্ট সব আপডেট করা আছে, যা ক্লাস হচ্ছে সবকিছু। What's this?
Sir,
Okay, these are the few topics that we have to cover for the waves chapter. Everybody can hear me, right? I mean, is the volume all right?
Yes, sir.
First of all, we have some definitions to take care of, which is very much seen from the models that we used to have. So we need to understand what is amplitude. It is defined as the maximum displacement.
স্যার বাতাস আসতেছে।
The amplitude of a certain wave is defined as the maximum displacement of the medium particle moves from its equilibrium position or from its stationary position or undisturbed positions. All of these three terms, equilibrium, stationary, undisturbed, pretty much mean the same thing. Or sometimes we also use the term mean position, which is basically the undisturbed position of the medium particle if the wave did not exist within the medium. You have to understand the way we define a wave is wave is a disturbance that transfers through a medium or without the presence of a medium while carrying energy and information from one place to another without permanently moving the medium particles. So there are multiple pieces of this whole definition. So I'm going to go through it again. Wave is defined as a disturbance that carries energy and information from one place to another place with the presence of a medium or without the presence of a medium without permanently displacing the medium particles. So if there is a medium present, as long as the wave exists within the medium, the particles are going to have some up and down oscillation type of motions. When the wave is done passing through the medium, the medium particles are going to come back to their original position and become stationary at those positions. So the wave will propagate from one place to another place. In this process, it will transfer energy and information, but it will not permanently displace the medium particles. This is one of the key definitions for waves. I didn't write the definition of wave over here because that's a pretty simple thing. Amplitude is defined as the displacement. This is a very important factor. Amplitude is a vector quantity. Maximum displacement of a certain particle from a equilibrium position, which means if we are trying to draw a displacement versus time graph, amplitude of a certain particle can be positive or negative. One thing that you need to make sure and not to mess up is that whenever any wave is passing through a certain medium, amplitude refers to the maximum displacement that a particle can have. The particle, an oscillatory particle, as the wave travels through a medium, can actually have a lot of different displacement. For example, let's say this is a medium particle. A wave is traveling through this medium from left to right. So I'm just showing you one particle over here, not drawing for the whole wave. Let's say this particle, as this wave travels by, this is the direction of the wave direction. Let's say the amplitude of this particle on top and the bottom positions are labeled as this. So this is the maximum displacement on the positive direction or above, and this is the maximum displacement on the negative side. So you have to understand that this is the maximum amount of movement, vertical movement, this particle can do as the wave travels through it at different time instances. The particle can exist anywhere on this line. What is really important, the general symbol that we use for displacement is x. This is the position where x equals to plus a. This is the position where x equals to minus a. You cannot mess up or you cannot mix up in your head or also in your writing these two words, displacement and amplitude. In many cases, when students are writing, they equivocally use these two words replaceably, that the displacement of the particles is a. That can be correct sometimes, or the amplitude of the particle is a or something else. That can be also correct sometimes, but you have to understand what you are trying to refer to. Are you trying to refer to the displacement of the particle, which could be any displacement within the movement space of the particle? Or are you referring to the maximum displacement of the particle when the particle is supposed to be at one of the terminal positions, above or below, or most left or most right, if we are considering a transverse longitudinal wave? So do not make a mix up of these two terms. Maximum displacement is defined as amplitude. All displacements are not amplitude. Maximum displacement is the amplitude. Anything that is not an amplitude, it can be other displacement, or generally we can call it a displacement, which I'm going to talk to you after a while. Hasan, just a second. আমি একটু ডেফিনিশন গুলো বলে দিই, তারপর তোমার কোশ্চেন নিচ্ছি।
Okay, sir.
The speed of the wave. So one of the key part that we need to understand, what we understand by the speed of the wave. Speed of the wave actually means the distance. Well, I have written speed, so I'm gonna define it as distance over time. If I wrote wave velocity, I would say displacement over time. The speed of a wave actually means the rate at which the energy passes through a certain wave in terms of distance over time. So one specific example that I can put by is that whenever we try to represent a certain orientation of a wave, we sometimes use the idea of wavefronts. Wavefronts are actually imaginary lines that is drawn through the same phase or similar state of the wave wave propagating medium particles, or particles which are in the similar state of displacement. That's if we draw some imaginary lines to all of those particles, we call them wavefront. For example, if we have a ripple tank, sometimes we draw concentric circles for a point deeper. So those concentric circles are typically drawn to the crest positions of all the water waves. And as the wave goes forward, we actually represent that those circles are slowly getting bigger. Practically, there exists no such circle over like this, but this actually shows us that what is the rate at which the concentrated energy of the crest position particles, where the GP concentration is the highest, that is slowly moving forward. So the wave speed actually represents that what is the speed of the wavefront through a medium, or sometimes it can also mean that the energy that is passing through the medium, what is the distance covered by that energy passing over time. So this is not going to be joule per second because it is speed, it is going to be meter per second, but the speed of the wave is not the same as the speed of the oscillating particle. These are the two things that you cannot mess up. Speed of the wave is the speed of wavefronts going from one place to another place. This is going to be the speed of the wave actually makes actual displacement. So the energy from the source actually goes from one position to other position. But as the wave travels by, the medium particles move up and down, or they oscillate. That oscillation does not cause the particles to actually physically permanently move from the equilibrium position. They have oscillation as long as the wave exists, and eventually they're going to come back to their equilibrium position when the wave is done passing through, or there is no more disturbance of energy within the medium. So speed of the particle and speed of the wave are two different things. There are some mathematics involved for this thing. I'm going to show you those mathematics as well, mathematical equations as well. So it will become more clear after a while. We all understand the very basic definition for time period. Time period is defined by the amount of time it takes for a wave particle to complete one full oscillation is defined as time period. One thing that you need to remember is that within the time period amount of time, any oscillating particle covers a total of 4a distance. 4a distance means, let's say if we consider the movement of an oscillating particle like this black line, let's say at t equals to 0, if we start to observe the particle which was exactly on the equilibrium position and started to go upwards, one full oscillation is completed when the particle reaches the same position of its motion from the same direction. So if you start to observe a particle's motion starting from the equilibrium going upwards, one complete oscillation will happen as the particle reaches all the way up, then falls all the way down. Whenever it's going to reach this equilibrium position, this is not going to be one full oscillation because we started the observation while the particle was going up. But while it goes all the way down over here, it is not going up, it is going down. So you have to continue the motion further. The particle has to reach all the way at the bottom. And then as it starts to go upwards, and eventually when it reaches this point coming from the underneath point, that is when one full oscillation would be completed. So if I try to draw this motion paths with individually different lines, actually they're going to be moving in the same path. But if I try to draw it in different lines, this is how I can draw this thing. For example, going up, going down, and then going down further, and then from here going up. The particle is not going to move in different vertical lines. I'm just showing you the different movement to represent the total amount of distance covered by the particle for one complete oscillation. So while it's going up, this is this distance covered is A, falling downwards back to the equilibrium, this is another A, going all the way down to the trough position is another A, and then going up to the equilibrium position once again is another A. So in a total amount of time T, the total amount of distance an oscillating particle covers is gonna be 4a distance. This is not essentially this is not exclusive for a particle observation from the equilibrium position. If you start to observe a position that for a particle that starts its motion from the terminal position, for example, in that case also the particle is going to cover 4a distance. If you start to observation for a terminal position, for example, let's say if you start to observe a particle's motion from the peak, it has to come down all the way, move all the way down to the trough, then reach up to the terminal position, then eventually reach up to the crest position once again, and that way it's also going to cover total 4a distance. So, and if it's also equally correct if you start to observe from any random position as well, that's also correct. It's going to work out just as much. Point that I'm trying to make over here, that in a total amount of t amount of time, any oscillating particle of the medium covers the total distance of 4a, where a represents the amplitude of the particle. One of the things that is sometimes we actually come across is that whenever a wave is gonna pass through a medium, is it always gonna have equal amount of amplitude on both positive and negative side? The answer is yes. As long as a certain wave passes through a fixed medium, not a changing medium. I'm gonna explain what a changing medium can be. As long as a wave passes through a fixed medium, it will always have the same amount of amplitude above and below the point. But if we have a changing medium, then the amplitude can have some variation. If you wonder what does that actually mean, I can bring about a small example that we have come across in our O levels. If you please remember, for the ripple tank, let's say we have the ripple tank's water level over here, and underneath this water we have a piece of glass block that is placed right over here. So let's say a wave is coming from left to right. What we've seen on our O levels that whenever the water is deeper, the amplitude is going to be bigger. When the wave becomes shallower, we're gonna the amplitudes are gonna be remaining same, but the wavefronts are gonna become actually closer because it's gonna travel from deeper to shallower medium. So that's one thing. The other thing is that amplitude of a certain particle is actually a very strong representation for how much energy that wave carries. Try to understand this part. Amplitude of a certain wave is a very unique, very prominent measure representation for how much energy does a wave carry. So if a wave has a much bigger energy amount, its amplitude would be definitely bigger. This is why loudness of sound is highly dependent on the amplitude of the source. If you have a big source that is making the sound, you're gonna have a louder sound, and vice versa. Now, one thing is very important, that whenever waves travel from one place to another place, as it covers through distance, for most cases, I mean, I'm going to say for almost, for almost every case, all case, I'm using the term almost because there is a small exception that is called laser. So I'm going to talk about that after a while. So uh, almost always, whenever they travel from one point to another point, the energy of the wave starts to spread out. This happens because of the type of the energy medium that we have, or sometimes this can also happen because of the medium particles that we have. So as the energy, as the wave slowly goes up, for example, if I try to draw up a certain scenario for you, let's say there is a lake, and let's consider this is a lake of equal uniform density, uniform depth of this thing. So it's like a circular tank or something like that. Let's say you are standing over here and you are pushing up and down a football at this point. So you're gonna producing circular waveforms going around all the way. So you're gonna have shapes like this, and these circles are gonna go outwards from these positions as the wave goes by. What is very important that whenever you are moving this ball up and down, let's say you are moving this ball up and down by providing a total, let's say you are doing a work equal of 100 watts. So every second you are spending 100 joule of energy to make the ball up and down. So this is the total amount of energy that you're transferring to the water molecules. So every second the water molecules which are right over here are receiving 100 joule. After when the wave is going to start to spread out, let's say after a certain time, let's after 1 second, if the wave within the water medium has a speed of, let's say, 10 meter per second, this is the speed of the wave. So let's say v equals to 10 meter per second. So after 1 second, this energy is going to spread out to a circular amount of length of 10-meter radius. Which what I'm trying to mean is that after we produce this wave, one specific wave or one pulse of the wave at t equals to 0 second, if the speed of the wave is 10 meter per second, after 1 second, it is going to be 10 meter away from the source in all direction. And what you need to understand that this 100 joule of energy that you provided to these water molecules right over here, this is going to get spread up in all of these water molecules in this 10-meter circumference path. The further time goes by, that same amount of 100 joule energy would be spread out into a much bigger number of particles because the wave is spreading out in a radial direction outwards, which basically means as the wave slowly goes outwards, it's going to slowly lose its amplitude. And this is basically what we see whenever we try to produce some water wave in a water medium. We don't see the wave actually exist for infinite distance. After traveling a certain amount of distance, the wave actually dies out. What actually happens in the process of spreading out the energy, the particles actually starts to receive less and less energy because energy is getting spread out. And also, as the water molecules move up and down, there is some lateral friction in all the water molecules. So try to think about it. If you consider a wave traveling by, let's say, if this is a water medium, and let's say if I try to zoom on to this thing over here to a very high, extremely high level, if you consider two water molecules which are placed side by side, there is going to be a little bit of phase difference between these two particles. So this is, so whenever this is going up, this is also going up, but this is slightly behind this particle. So at that tip, there's going to be a little bit of dissimilarity. So these two particles are going to be pretty close to each other. They're going to move in conjunction with each other for most of the time, but pretty much at their terminal position, they're going to have a little bit of vibration. And this is actually true for all the water molecules which are undergoing the oscillation through this particle. So there are layers of individual water layer, vertical layers are going to have some friction with the neighboring layers, and that friction also causes the wave energy to get absorbed within the medium as heat energy. Now, heat is actually not a very heat energy of a certain medium doesn't cause any very specific type of movement of the particles. It actually produces a random vibration and translation movement of the particles, unless there is a convection current. Convection current produces due to pressure difference. That's a different scenario. So naturally, whenever heat is absorbed within a certain medium, the particles start to produce random motion. So the orderly motion of a wave, that the particles are synchronously going up and synchronously going down, this slowly becomes less prominent, and eventually all the energy can be converted in within the heat energy of the medium, and that's when the wave will be completely not observable anymore. That's what happens for a physical medium presence. If we do not have a physical medium, for example, let's say we consider that a star is within the void of the whole galaxy, space. Let's say within the space there is a lonely star. Consider that this is the only star there is, and there is no other planet around. So consider this as an isolated system. A star is, let's say, producing energy at, let's say, 1 million watt. It is producing 1 million joule per second, and is spreading out that, radiating out that energy in the form of light and heat. So as the energy is going to spread out radially in a three-dimensional space, so that energy is considered to be spread out as radially outwards as a spherical manner. So as if there is no physical medium, the energy will not be actually converted into something else. But as the wave slowly travels further and further away from the sphere, the same amount of energy would be spread out over a larger and larger amount of spherical dimension, because you are slowly getting further away. That is going to cause the intensity or the energy available of the or power per area for that star is going to become slowly less. So the farther we go out, we're going to receive a smaller and smaller and smaller and even smaller fraction of energy the farther we get away from the star or from a source. So for those kind of scenarios, the actual amount of energy coming out from the star, even no matter how far you go, will never be zero, because there is no physical medium that is responsible to cause the energy to be converted to something else. The amount of radiation energy and the light energy, heat and light energy, they would always have some minimal value because they are traveling through the void of the space. But because they are spreading out, they will definitely slowly become weaker and weaker the farther they are going to get away, because of the spreading effect. So this always happens for wave sources, and this effect is sometimes called attenuation. The spelling goes like this. This is a term that we have to understand, because we're gonna deal with this thing in our discussion after a while. For some graphs, we're gonna have this attenuation. Attenuation is basically referred to as the gradual decrease of a wave's energy as it travels from one point to another point, due to the spreading out effect and also due to the absorption of the physical medium, if there is a physical medium present. So primarily the spreading out is the key factor for attenuation, and if there is a physical medium present, that also absorbs some of the energy. That also
Sir, can you repeat the pronunciation?
attenuation.
Atti-
Attenuation. Attenuation.
It is a gradual decrease in the size of the wave, sir.
It is a gradual decrease of the energy content of a wave while it is slowly getting farther away from the source. Hasan, you had a question. Please go ahead.
স্যার ওইটা অ্যান্সার হয়ে যাবে, আর একটা কোশ্চেন আছে স্যার।
Hello?
স্যার একটা ওয়েভ তো টেকনিক্যালি দ্য মুভমেন্ট অফ পার্টিকলস আপ এন্ড ডাউন মুভ করতেছে টু ট্রান্সফার এনার্জি টু এ ডিরেকশন পারপেন্ডিকুলার ফর ট্রান্সভার্স ওয়েভ। স্যার ওইটা যদি হয়, এনার্জি যদি এভাবে পার্টিকেলগুলো আমি যখন এনার্জি মুভ করি, এভাবে মুভ করে আর দুইটার মধ্যে ফ্রিকশন হয়, তখন তো এনার্জিটা হিট এনার্জিতে কনভার্টেড হয়ে যায়,
Yes.
তাই না স্যার? বাট হিট এনার্জি ক্যান বি হ্যাভ মাল্টিপল ফর্মস, রাইট স্যার? যেমন ইনফ্রারেড ওয়েভস, মাইক্রোওয়েভস, দে অল হ্যাভ সাম ফর্ম অফ হিট অর ইলেকট্রোম্যাগনেটিক ওয়েভস। এই যে ফর্ম অফ হিট বা এই যে এনার্জিটা কনভার্টেড হয়, এটা তো আর্থের আউটওয়ার্ডস চলে যায়, তাই না?
Okay, yes, so far yes.
সো মানে তাহলে তো ওয়েভটা ইভেন্চুয়ালি তো ডাই আউট করে ওই স্পেসে।
Well, if it is only space, it's not going to die out completely, because what I'm trying to mean is that as long as the spread out energy, which is light or heat energy, or I mean, what I mean is that electromagnetic energy form. Light is the visible spectrum, and infrared is the right after that the heat energy spectrum. So as long as the the energy format is within the form of electromagnetic waves, we consider the wave still is existing. It might have a smaller energy content the further it goes from the source. For example, let's say if this is the source, if the energy is spreading out in all directions, so at this point you're gonna receive a certain amount of energy on a certain square surface area. If you go over here, you're gonna receive a much smaller amount of energy. If you go further, you're gonna receive even smaller amount of energy, where all the surface areas are exactly equal. So the point that I trying to make that if it is considered within a space without the presence of any physical medium, you are not going to have a complete zero. It's going to be very small, it can be very minuscule, but it's not going to be mathematically zero. But if there is a physical medium, there would be friction, and eventually you can have it to actually come to zero. The electromagnetic wave can actually die completely. Die actually in this case mean the energy is not getting destroyed, it is getting converted to some other form. Most predominantly it converts into heat energy of the medium particles.
স্যার আরেকটা কোশ্চেন করতে পারি?
Yes.
স্যার একটা ওয়েভ যখন যায় ওটা তো আমরা জাস্ট ভিজুয়ালাইজ করি, একটা ওয়েভ ইউজুয়ালি মাল্টিপল ওয়েভ প্রডিউস করে না যদি একটা বল মাটিতে টাচ করে?
um It depends upon the source that we are observing. For most natural sources produces a series of waves in a single go, but we can cause objects to produce pulses. Pulses are actually exactly one wavelength of wave is called a pulse. So just one pulse is this much is one pulse, or maybe you can consider this much is one pulse. Just one full wavelength can be also sometimes generated from a certain source. That is also possible.
স্যার পার্টিকেল গুলোর মেইন পজিশন যদি সেম থাকে ডিফারেন্ট থাকে তাহলে হাউ ডু দে কোলাইড স্যার? তাহলে নাকি নিচের পার্টিকেল গুলো যেগুলো আছে ইন্টারমিডিয়েট নিচের পার্টিকেল ওগুলোর সাথে কোলাইড করে?
If you try to visualize this thing clearly, for example, let's say let me just give this idea to you. Let's say there are 10 particles over here. So 1 2 3 4 5 6 7 8 9 10. Let's say there are 10 particles over here. Let's say these 10 particles are going to produce a wave. So when the wave is going to be produced, let's say for one full wavelength, these particles are all going to be spaced up like that. Okay, so I have to draw these particles in an orderly fashion over in different positions over here. So that's 1 2 4. I am needing more than 10 because this path is longer. So what I'm trying to mean is that if you consider the position of two particles, neighboring particles, they're not in the same position, right?
জি স্যার, সেম পজিশনে না।
So this one will rise up to the peak. If the wave is going this way, this one will rise up to the peak a bit earlier, this will rise up to the peak a bit later, right?
জি স্যার।
Close to at the end of their journey position over here, there will be a certain position where these two particles are, for a small duration of time, they are going in opposite direction, right? For most of the
Yes, sir.
part, they will be
ওইটা তো নিচে নামবে তখনই উপরের দিকে যখন ইনস্ট্যান্টেনিয়াসলি জিরো হবে তখন মানে অপোজিট ডিরেকশন হয়ে যাবে।
Exactly. So for that small duration, you get a little bit of friction. And if you consider the friction between all the particles, which is actually, I'm over here only to show you the particles which are only on the surface. But when a wave is not created only on the surface, there are series of particles underneath as well, right? So all of these particles are rising up and all these particles are going down. So there is a lot of motion going by, and all of those internal collisions, sliding effect of the particles lead to friction.
জি স্যার, বুঝছি।
Any further question, anyone?
Yes.
So এটা গেল একটা জিনিস। So আরেকটা জিনিস যেটা আমাদের বোঝা লাগবে ক্লিয়ারলি, সেটা হচ্ছে টাইম পিরিয়ড ইজ the amount of time within which a certain particle covers for a distance. I was talking about, was I talking about phase or wave front? What was I talking about? I was talking about attenuation and then energy content of the wave. Okay, let's get back to the definitions. I'm gonna get back to the whole.
Sir?
Yes.
So worksheet problems গুলোকে আমরা কোনো এক্সট্রা ক্লাসে সলভ করব?
বুঝি নাই
স্যার, আমাদের লাইক আগের ওয়ার্কশিট গুলো প্রবলেম স্যার, ওগুলা স্যার আমরা কোনো এক্সট্রা ক্লাসে সলভ করব?
না, আগের ওয়ার্কশিট গুলো পড়ার সময়ের জন্য আমি তোমাদেরকে এই টাইমিং এই ক্লাস টাইমিং দিব, আর হচ্ছে প্লাস তোমাদেরকে আমি এক্সট্রা ক্লাস দেওয়ার কয়েকটা schedule করছি। I'm going to discuss those times with you as well. আর হচ্ছে হোপফুলি সামনে যদি আচ্ছা কাছাকাছি সময় আমাদের গভর্নমেন্ট হলিডে আছে কবে, যেদিন স্কুল বন্ধ থাকবে?
স্যার দেখতে হবে স্যার, 1 মিনিট স্যার।
If you have any government holiday coming by, then I'm gonna take. I can try to get a long class in the morning for workshop selection. I mean, I'll be available. You can drop in at your convenience and show me your troubles. Maybe 2-3 hours long class or longer than that. Maybe 9 to 1, something of that format. I'll be available, but you can join in at your convenience and show your problems in which you give. Problem solving class in class. That can also happen.
Yes.
Continue with the waves lecture. So time period is also has a very important scenario, significance is that within the amount of time of a one-time period, wave covers the total linear distance of lambda. So this is another important factor. So whenever the wave travels within the amount of time period, one oscillating particle completes one full oscillation, and the wave itself covers a specific amount of 1 lambda distance to the in the duration of the wave. Why does that happen? I mean, if I try to show you a little bit of animation for that, I can actually try to, maybe I can show you, actually have the just a second. Okay, we have this. This is a scenario. What is I going to? Acha, I would like to show you. Acha, I would like to have a loose end, no end. So if I allow exactly one pulse, let's say, or if I make it to oscillate a bit slowly, how can I have a slow motion? So what do you need to see? I can pause. Let's say we're gonna start to observe this starting from one particles, exactly starting from the beginning. Let's say here is the motion. So one full oscillation, one full time period will happen when this particle will go all the way down and eventually to rise up back over here. I want all of you to have a good look. Actually, I don't want any damping over here. So wait. What I want all of you to see is that boom. So what I want you to see that when this particle completes one full oscillation, this crest position is going to travel exactly one wavelength. Have a look. The particle is going down, then the crest is moving to the right. So if I move it more, and a little bit more, perfect. So you can see that when one oscillating particle completes one full time period, the wave actually covers exactly lambda distance. This is actually the very fundamental theory, or this is actually by definition actually also happens, and this is also the very basic by which the equation v equals to f lambda comes into existence. The equation goes like this: that within t amount of time, the wave covers lambda distance. So within unit time, the wave covers lambda divided by t distance. By definition, the distance covered within lambda divided by t is called the speed of the wave. So v is actually lambda over t, and also by definition, we can also write 1 upon t as frequency. So that ultimately gives us v equals to f lambda. That is a very common equation that we go by, which comes from here. So I'm going to extend this relationship that I just wrote over here by a bit of an arrow. What you can see over here, I did not use equals to sign. I'm using a double-sided arrow just to represent that these two amounts of measurement. One is time and the one is length. They are directly related. So if you are talking about for half the time period, you're gonna this is gonna be clear. So if I just extend this part, I can write that time period amount of time is relevant to 4a amount of distance covered for the oscillating particle, which is also relevant to lambda distance covered by the wave, and which will be also related to a total of 360-degree phase, 360-degree or 2 pi, if you consider radian, amount of phase for a certain oscillating particle. This four-part relationship is going to prove very helpful for the upcoming discussion of superposition and also for the progressive and the stationary waves figure judgment. It's going to be very helpful for us. So we're going to use it pretty often for the upcoming part of the lecture. And then we have wavelength. I just discussed what the wavelength is. One of the important part that I would like to discuss before I go for the wavelength is what do you mean by phase? In your O levels, the wavelength was defined as the distance between one crest to the next crest is, or one trough to the next trough, or one compression to the next compression, and the one rarefaction to the next rarefaction for the case of longitudinal waves for the last two. So that much distance is defined as a wavelength for your O level syllabus. Well, to tell you the truth, wavelength is not exclusive to those distances. Wavelength actually can be considered for the as the distance between. Once again, wavelength is not vector. Wavelength is a length, so it is a distance. Be careful not to mess up amplitude and wavelength. Amplitude is a displacement, maximum displacement in one direction. And wavelength is a length. Wavelength is a length between two consecutive particles which have the same phase, which brings us to the concept for what do we mean by phase. Now let me show you the definition of phase, and then I'm going to try to explain how much of the idea of phase is actually necessary for your syllabus.
স্যার
Yes.
ডেফিনিশনস গুলো কি লিখে নিব?
না, ডেফিনিশন লেখানোর কিছু নাই, ডেফিনিশন সব তো আমাদের বইতে আছে।
আচ্ছা স্যার, আপনাদের বুকলেট দিলেন না, নাম্বার 6 এ লেখা BAAD, এটা কি?
Okay, this is actually a very beautiful answer. Have a look. Phase with vertical vibrating particle at any instant is a physical quantity which completely expresses the position and direction of motion of the particle at that instant with respect to its mean position. This is actually pretty complete definition, that a phase actually primarily consists of two specific information. It is consisted of that where that particle is in its path. I mean, considering that the equilibrium position is equal to x equals to 0. Where is the particle currently located at any instant of time? Where is the particle? So is it above, or does it have a positive displacement, or does it have a negative displacement? That positive or negative consideration can tell us that where the particle, on which side the particle is located, and also it can tell us that how far away from is the particle from its mean position or equilibrium position. So that position information paired with the velocity information. Two things. So the position information, the velocity information, combinedly, these two things make up the phase information of a certain particle at any instant. For the sake of simplicity, for your syllabus, the position information is not considered to be really highlighted. For your syllabus, the way CAE syllabus handles the term phase is that we're going to mostly be dealing with direction of the particles for most part, at least for the requirement of understanding the, I mean, the velocity direction of the particles are going to be representing the phase of the particles for most cases, specifically for stationary waves. But for progressive waves, you can have a little bit of difference. So what I want you to understand, if I just try to show you this thing,
স্যার,
yes,
আপনি যে বললেন না প্রোগ্রেসিভ এর জন্য ডিফারেন্ট হবে, কি ডিফারেন্ট হবে একটু বলবেন আবার?
the idea of
মাত্র যে
phase, the definition of phase.
ও আচ্ছা,
Okay, One of the things that I would like to clear out, if we consider a certain wave, there are a few other things that I'd like to tell you before I'd like to actually clear up before I get into the whole discussion of waves. One of the thing is that you can come across a lot of different waves, a lot of different graph expression for a certain waves chapter. For example, you can have, if we have displacement versus distance, let's say you have a shape like this. This shape is actually the side view of a certain wave for a still picture. So what I'm trying to mean is that this is the position of all the particles of the surface of a wave, or maybe of the medium. It can be a string for all I care. Not necessarily, it doesn't have to be the water medium. It can be a string that is undergoing oscillation. And let's say you took a picture at a certain moment of time of the whole oscillating string, and you just took a still picture, and this figure, when its displacement over distance, is representing all the particles of that medium at their position at that time instance. So in this case, time is not a variable. This is for a fixed time where all the particles are visible. So actually you can see this particle is over here, this particle is over here, this particle is over here, this particle over here. So we have individually different position for all the particles. However, there are certain particles which are in similar position. For example, the two case particles we consider, they are both at the highest position, highest maximum position, highest positive displacement from the particle, from the equilibrium position. So we can consider them to be particles with the same phase. Point to be noted, because this is a very much like a sine curve, we can also represent in some cases this graph to look like this. Let's say displacement versus phase angle. Let's say I'm going to write it in degree. So if we drop like that, let's say this is our zero position, this is 180, this is 360, this is how much is that? 360 plus 180 হচ্ছে কত জানো? 540. And then if it goes over here, we can have 720 over here, and so on and so forth. So one full cycle is represented as 360 degree, and so this also means that whenever you have two particles of the same phase, maybe two phase particles or two trough particles, the phase difference between these two particles is considered to be 360 degree, or sometimes the phase particle difference between two similar phase particles is also considered 0 degree. What I'm trying to mean, particles which have a same phase difference of 0 degree or 360 degree or 720 degree or something of that sort. Practically, this is n into 360 degree. We write the value of n equals to 0, 1, 2, 3, dot, 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 dot. For particles which have a phase difference like this, they can be all called particles with the same phase, which basically means their movement is synchronized. This is the key part that I really want you to appreciate. It means that their movement is synchronized. What I'm trying to mean is when this case particle is start to go down, this case particle will also start to go down. When this particle is going to be reaching over here and going downwards, this particle will be also in this same point, which means these two particles are always going to move in perfect synchrony or perfect synchronization with each other. And these two particles can define as to be same phase particles or identical phase particles. They have zero phase difference. Sometimes we can call it them to have n into 360 degree or n into 2 pi radian phase difference. Same phase particles are actually more of the common term. For example, if we just have a look at this phase simulation, and if I play over here, if actually, let me just pause it a little bit. If you should see actually the way they've used green dots over here, but can we use them for some reference? Actually, would be useful. If I want to, okay, if I want to reduce the wavelength, I have to increase the frequency, right? Frequency can I make? So need a bit more. So Okay, now we are getting it. Have a look. All of these green particles are moving up and down synchronously. So we can say in this case, these green particles are in phase. And all the first particle after on the right of the green particle, they're going to be in phase with each other. So this is basically what we mean by same phase particles. So yeah, we could achieve this somehow. This is nice. This is what I mean by same phase. So, or other words, when you pause this thing, you should see. You can also say that all these green particles are in phase because their motions are perfectly synchronous. So you can see that they're all moving up. They're all reaching their maximum position at the same time. Then they're all going down at the same time, and then they're all coming to the bottom position or the top position at the same time, and they're going up at the same time as well. So their motions are perfectly synchronous. We say these particles are in phase. So the gap between two consecutive same phase particles. So for example, from here to here or from here to here, the word synchronized or next is very important. I have to say that the wavelength can be defined as the distance between two identical phase particles which are next to each other, or you can say two identical phase particles which are consecutive. Consecutive means this and this. The gap between these too much is how much is one wavelength, or the gap between these too much. You have to understand, if you don't use the word next to each other, or if you don't use the word consecutive, it might actually mean that the gap between this particle and this particle, which are also in phase, this much is one wavelength, but that's not the case. This much happens to be two wavelength. If you go further, that much would be this much from here to here, this much would be three wavelength. So the word consecutive is very, very important. Do not miss upon this one if that definition ever comes in your exam. Sometimes actually the examiners check out for this small tiny bit of word cautiousness from the students in the multiple choice answers. They give you a lot of different definitions, and sometimes they just take out one single word out of the definition, which makes it imperfect. It would visually appear to be very much correct, and you would be very much what can I say, inclined to choose it as a correct option, but be careful not to fall in those traps. These are questions to check your understanding to a very precise level. So be careful about those. So that's the very basic idea for phase particles. And
Sir.
yes,
আমি একটু আপনার N360 অ্যাঙ্গেল বুঝতে পারলাম না একটু অ্যাঙ্গেল জিনিসটা
আচ্ছা, এটা হচ্ছে
যে
আমাদের এই ভ্যালুগুলোকে ইন জেনারেলি এক্সপ্রেস করার একটা নরমাল ওয়ে। whenever we have a lot of different value, for example তোমরা সেট পড়ছো না, তোমরা সেট পড়ছো এই পর্যন্ত কোথাও?
জি ভাই ও লেভেলে সেট করছিলাম।
আর মনে করো একটা সেটকে লেখার প্রসিডিউর কি, মনে একটা সেট কেমন হচ্ছে, let's say a certain set A is represented as x belongs to real numbers, whereas real number are line দুটা থাকবে, whereas let's say x let's say 2 less than x less than 3. And এটা মানে কি? এটা মানে হচ্ছে all the numbers which are bigger than 2 and less than 3, all real numbers which is practically infinite numbers, they belong to this set, তাই না? তখন আমি সবগুলো রিয়েল নাম্বারকে একটা করে লিস্ট না করে এটা লিখে আমি অনেকগুলো রিয়েল নাম্বারকে একটা সিঙ্গেল লজিক দিয়ে এক্সপ্রেস করলাম, ঠিক না? ইউ ডু আন্ডারস্ট্যান্ড হোয়াট
জি
দিস?
ভাই
সো এখন এখানে n * 360 ডিগ্রি এক্সপ্রেশনটা হচ্ছে আমাদের এই সবগুলো যে পসিবল নাম্বার এখানে হতে পারে 727 বা 1080, তারপর আরেকটা 360 ডিগ্রি প্লাস আরেকটা 360 প্লাস, এখানে অ্যাকচুয়ালি অনেকগুলো নাম্বার হতে পারে। আমরা সবগুলো নাম্বারকে একসাথে লিস্টিং ভাবে না লিখে একটা জেনারেল এক্সপ্রেশন দিয়ে লিখলাম that this all of these numbers can be represented as n * 360 degree, where the value of the n is equal to 0 1 2 3 dot 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 0 থেকে স্টার্ট করতে হবে, কারণ হচ্ছে আমাদের এখানে 0 ডিগ্রি ইনক্লুড আছে। সো আমি n হলো 0 বসালে 0 * 360 ডিগ্রি 0 ডিগ্রি পাবো, n হলো 1 বসালে 1 * 360 ডিগ্রি 360 ডিগ্রি পাবো, 2 বসালে 720 ডিগ্রি পাবো, 3 বসালে 1080 পাবো, এমনি করে আরো আসতে থাকবে। So this is a way, this much, this all of you have to write all of this part. You cannot only write n = 360 degree. You have to define what this n mean in terms of number. This is a simplified way to represent all of these numbers without actually trying to write all of them.
বুঝতে পারছি স্যার, থ্যাংক ইউ।
So এটা গেল একটা জিনিস, the idea of phase. আচ্ছা, আমি phase এর আইডিয়া আসছিলাম হচ্ছে wavelength থেকে। Then we have the frequency. If you do understand what a frequency of a certain wave is, frequency of a certain wave is basically represents the number of complexes which are oscillating particle completes in unit time. In SI unit, you can also say in 1 second. That is actually hertz. But in unit time is the very basic definition. Then, if you want to use a quantity, a defined unit, you can say in 1 second. That also works for the definition of frequency. Frequency of a certain wave, very important. Frequency of a certain wave is exclusively dependent on its source. Frequency of a certain wave is not dependent on anything else. Whenever a wave is produced from a certain source, its frequency is fixed then and then. No matter what you do to this wave, no matter what medium you make it to pass through, no matter how many mediums you make it to pass through, as long as that wave exists in the wave form, or this amount of energy exhibit itself as a wave, it is going to have the exact same frequency. If we change the medium, if we change it to undergo, if it undergoes diffraction, polarization, or whatever, no matter what wave phenomenon that will make a certain wave to go through, you can make changes to its amplitude, you can make changes to its wavelength, you can make changes to its speed. What you cannot make changes to is its frequency. Frequency of a certain wave is an unchangeable property of that wave, which is exclusively dependent upon the source from which that wave is created. Then comes the idea of wavefront. Wavefront of a certain wave. I just discussed what the wavefront is. It's an imaginary line drawn through all the same phase particles of a wave, and then I also discussed the part of the phase. Any questions so far for the basic definitions? This was a quick brush up for the O-levels part, and also the additional things that you have to understand with the O-levels part. Using all of this information, I actually brought about this 4-part information. I prefer to write them as a double arrows. You don't ever have to write this information, but I want you to understand what this actually means. This is very helpful for mathematical calculations, which you're going to see in a while. So don't worry about that. Any questions so far?
স্যার
হ্যাঁ, বলো।
একটা ওয়েভ যতটা ডিস্টেন্স ট্রাভেল করতেছে টাইমে ওঠাছে স্পিড নাকি?
Yes, this is what
Like-
yes.
আর এটা একটা জিনিস, আর হচ্ছে ওয়েভটা যে অসিলেট করতেছে এটা আরেকটা জিনিস নাকি? লাইক ওয়েভ স্পিড এন্ড দ্য অসিলেশন ইজ ডিফারেন্ট নাকি?
Exactly.
আচ্ছা স্যার।
সার্টেন এক্সাম্পল দিয়ে দেখাই, সার্টেন একটা এক্সাম্পল দিয়ে দেখাই। মনে করো আমি এখানে ওয়েভের ফিগার আঁকতেছিলাম, তো আমাদের কোন এখানে আমি ফিগার দিচ্ছিলাম যে this is the certain situation for a wave where we have taken a image or still picture of a certain wave propagating medium, and this represents all the individual different particles. This is one way to represent a certain wave. There is another information that we can also do. Let's say we are going to focus on a very specific particle on the wave. Let's say we're going to focus on this particle on the wave, and we're going to observe this one's motion with respect to time. So try to understand what I'm trying to say. We are not going to observe all the particles. All the particles' motion are somewhat similar but not identical, because they are not moving in perfect synchrony with each other. We have sensuous particles after every lambda distance, but in between those two, in between one wavelength, the particles have different type of motion. They are somewhat slightly different, but they have similar motion. You can define all of their motion by using a sign ratio, because they are periodic and repetitive, which is also periodic. Actually, I use both of these words. Anyway, so let's say we're going to observe, we're going to pinpoint one specific point on this medium. Let's say if this is a rope medium, we can put a knot over here, we can put a shiny marker over here and observe its motion by a high-speed video camera. And let's say what we're going to do, we're going to plot this particle's vertical movement. Let's say this is the total amount of vertical movement that you can possibly do from here to here. So we're going to record this, and which we're going to plot this, all of this displacement of this one particle over time. We're going to do that. We're going to also come across a perfect sine curve. Actually, we're going to come across a sinusoidal curve, which can be a sine curve, which can be a cos curve. A cos curve is also a sinusoidal curve. One thing you need to understand is that this word sinusoidal actually means a curve which has a shape like a sine curve. You need to understand that a cos curve also has the shape of a sine curve, right? What is the difference between a sine curve and a cos curve? A 90-degree shift.
Cos 0 1.
A 90-degree shift, right? বুঝতে কি বলছে? বুঝো নাই?
Yes, sir.
যারা বুঝো নাই তাদের জন্য দেখাচ্ছি। হ্যাভ আ লুক। মনে করো এটা হচ্ছে একটা সাইন কার্ভ, ঠিক আছে? আর এটা হচ্ছে একটা কস কার্ভ। আমি যদি এই সাইন কার্ভের এক্স্যাক্টলি এই জায়গাতে এক্সিসটা আঁকতাম, তাহলে এটা কস কার্ভ হয়ে যেত না? এই ওয়াই এক্সিসটা যদি এখানে হতো, তাহলে এখান থেকে তুমি তো অবজারভেশন শুরু করো, তাহলে এইটুকু পুরোটা কস কার্ভ হয়ে যাচ্ছে না? You might wonder এটা পসিবল কিনা? Well, possible কিনা?
Yes.
Possible সেটা পরে বলতেছি, but if I chose to draw this y-axis exactly on this point, then wouldn't this whole part become a cos curve very much like this one? The answer is yes. So any graph that has a shape like a cos curve or a sine curve, maybe this is not starting from the peak as well. You can also have some wave starting from halfway point, maybe something like this. This is also a sinusoidal curve. This is not a perfect sine curve, nor this is a perfect cos curve, because the starting value is not 0 or not 1. But the shape is periodic, so that's why we can call it to be a sinusoidal. This is the word, SINUSYDAL. Sinusoidal curve means a curve that appears to be like a sine ratio, or it can be expressed using the sine ratio of trigonometry. So a sinusoidal curve, we're gonna get if we draw the distribution information of this one particle with respect to time, we're gonna come across the sinusoidal wave as well. And what is important for you to understand that whenever we have this distance on the y-axis, this much represents lambda. Whenever we have time on the x-axis, sorry, I said y-axis, x-axis, this much is going to represent one time period, because this is time axis, so you cannot get lambda over here. So be careful to choose these variables very carefully. You know this is from your syllabus. I'm just trying to brush up your memories a little bit so that you do not forget, do this silly mistakes while you're solving your MCQ paper, and thus become slightly disheartened. I should play and everything. So trying to have both ends covered.
So green গ্রাফটা কি মানে একটা পার্টিকুলার মুভমেন্টের গ্রাফ?
একটা particular movement pattern drawn over time. So this is one particle observed and plotted. The distances are plotted over multiple time instances. Right. This is the view of the entire medium for a split, not a split second, for an instance of time. This was the frozen time view of the medium. This is a continuous movement of the particle with respect to time. You have to understand one thing: the particle is simply going up and down, but a particular individual motion position যদি আমরা টাইমের রেসপেক্টে প্লট করি, টাইম তো আস্তে আস্তে সামনের দিকে যাচ্ছে, তাই না?
Yes sir.
একটা ভার্টিক্যাল লাইনে মুভ করতেছে, বাট সেটা যদি আমরা টাইমের রেসপেক্টে প্লট করি, তখন আমাদের কি হবে? আপ এন্ড ডাউন মোশনটা আস্তে আস্তে কি হবে? টাইমে মুভ করা শুরু করবে, ঠিক না?
Yes sir.
That's what we are saying over here, that this is a time plotted graph for a single particle. To be honest, if you plot up all of the particles movement, we're going to come across exactly similar curve. All of those curves would have the same sinusoidal curve with the same time period, same frequency and everything. Only individual different particles, if all of them plotted on the same point, are going to have slightly different starting point. এটা কেন হবে? কারণ সবগুলা পার্টিকেলের ফেজ এক্স্যাক্টলি সেম না। এই পার্টিকেলগুলোর ফেজ সেম, বা এই পার্টিকেলগুলোর ফেজ সেম, but you can say this one and this one has the same phase, but this one and this one has a bit of a different phase. So they are going to have similar curve, but they are not going to have identical curve. Do you understand my point?
জি স্যার।
এটা গেল। এরপর আমাদের যে জিনিসটা লাগবে সেটা হচ্ছে যে what are the different type of waves that we have to do. Mechanical waves are those which necessarily require a physical medium to propagate from one place to another place. The most common example is sound wave. Then you can talk about any medium-based wave named by the medium. For example, water wave. You can say glycerin wave. You can say a glass wave. You can say what is the wave that is called that comes out of an earthquake? It's not called earthquake wave. It has a different name. Whatever, it has a medium-based name. So waves which essentially require a medium are called mechanical waves, and waves which do not require a medium, but if there is a medium, they can selectively pass through it, depending upon the medium and the type of the wave. Those are called electromagnetic waves. So medium required, definitely required or not, based upon that we can have mechanical waves or electromagnetic waves. Then you can have longitudinal waves and transverse waves. You know what this is. Longitudinal waves are those where the oscillating direction or the velocity of the oscillating particle, I can say actually velocity, the velocity direction of the oscillating particle is parallel to the direction of the wave velocity. So in other terms, I can say the direction in which the energy of the wave is passing by. In longitudinal wave, the particles oscillate parallel to that direction. Whereas for the transverse wave, the direction of the wave energy passing is perpendicular to the direction of the particles oscillation. So for longitudinal waves, let's say this, if I try to draw the view, let's say this is the direction of the wave speed energy. Wave energy is passing in this manner. For a longitudinal wave, the motion of an oscillation is going to be like that. It's going to be parallel. So you can have another particle right over here. This is also possible. You can have another wave particle over here. Simply the wave direction and the oscillating particles velocity are going to be parallel. Whereas for the transverse wave, the wave direction and oscillating particles velocity are going to be perpendicular. Now this perpendicular can be in a lot of different orientation, which actually brings us to the idea of polarization. So we're going to talk about polarization as a side. এই লিস্টে পোলারাইজেশন লিখতে ভুলে গেছি, আমাদের পোলারাইজেশন নিয়ে কিছু পড়াশোনা করা লাগবে। And then also we have Doppler effect. Doppler effect লিখতে ভুলে গেছি। Doppler effect. Doppler effect is actually pretty interesting. Okay. So these are the two type of waves that we have. Then we have another two different type of variation for progressive wave and standing or stationary wave. Progressive wave is the type of wave that only carries energy in one direction. For example, let's say I'm making a sound and you're hearing it. There is a lot of different conversion medium. I have the microphone. There's a little electrical pulse passing through my computer, which is traveling through the fiber optic backbone, reaching up to your computer. Eventually, your speaker or your earphone is making the sound and reaches to your eye. But this is a one-way path, which means I'm making the sound. The sound is eventually reaching to you. There are different medium involved. So whenever the energy of a certain wave is only traveling in one direction, that's what we call a progressive wave. The idea of standing wave or stationary wave is that whenever two waves, let me just give you the basic idea first, then I'm going to go to the individual different key segment of the definition, because those individual key segment actually are important for the definition. The idea of stationary wave is very simple. Whenever you have two similar waves, I'm not using the term identical, when we have two similar waves coming in opposite direction and they both merge into one, or in a more physics-based word, we say they superpose onto each other. They together they produce a certain specific type of movement of the physical movement of the medium particles. Or if you don't have medium involved, for example, if we're dealing with electromagnetic waves, in some places you get a very high intensity or very concentrated energy form. In some other places you get very low energy concentration. So those points are called antinodes and nodes, which are gonna see after a while. But the idea is that if you have two similar waves crossing into each other from opposite direction and they meet at the same time with each other going into opposite direction, in that case the total amount of energy transferred through those pair of waves is actually zero, because the amount of energy transferred from, let's say, left to right is counterbalanced by the amount of energy transferred by the wave that is traveling from right to left. So the total energy transfer will be zero.
Can you please repeat, sir?
Whenever we have two similar waves going in opposite direction, meet with each other or superpose with each other, the total amount of energy transferred would be zero, because one wave is, let's say, traveling carrying energy from left to right, the other wave is carrying energy from right to left. If they are actually meeting onto each other, the total net amount of energy transfer will actually become zero. They can still transfer energy from one place to another place individually, but the total amount of energy transferred would be actually zero. So that's that kind of a composed wave, or what I can use another term, let's say mixture wave, or maybe a resultant wave. This is not a keyword. The total superposed wave, the outcome of the superposition of the two individual waves, that thing is what we call a standing wave or a stationary wave. Now, interesting for you to understand, the stationary wave can have a lot of long discussion, which we do not have for a very long discussion for our syllabus. We have a very simplified version for the graph and for the variation. But still, just to make sense with you for what can happen, and I mean, just to cover the gray area of the syllabus, in my opinion, I'm going to go a bit further from what your syllabus specifically asks us to learn. So I'm going to cover that part as well. Let me discuss the small, tiny, important parts which are actually needed for the definition or for the concept of stationary wave. One thing that we need to understand, that the two waves which should superpose into each other, they have to be of similar type of wave. For example, you can merge a light wave with another light wave. You can merge a sound wave with another sound wave. You can merge microwave with another microwave, but you cannot merge an electromagnetic wave with a sound wave. If you have these two waves, let's say on one side you have a light source, opposite to it you set up a loudspeaker, produce two waves across each other, you cannot expect them to superpose onto each other. They have to be of same type of waves. This is very important, like super very important. Similar waves, similar type of waves has to superpose on each other. You cannot have dissimilar type of waves. That's not going to work out. Point one. The second point is that they have to physically meet in a single space, in the same physical space. What I'm trying to mean, let's say you're trying to produce superposition of waves by means of, let's say, monochromatic light source or a single color light source. So let's say you have one light source over here on the left and the light source over here on the right, and you are trying to produce a superposition of waves in between. Let's say you are trying to achieve that. It is important that both of these light sources should be aimed at each other. If you place them slightly offset of each other so that the light rays are going parallel to each other, so they're practically opposite to each other, but they're not actually meeting each other somewhere within their path, you cannot expect superposition to happen. So they have to physically meet each other at a given time in the physical space with each other. That's important. So first point, they have to be same type of waves. Second point, at a given point at a given time, these two waves should meet each other or superpose or merge with each other in the same physical space. The third point, which is important, that is, if we are dealing with longitude, if we're dealing with not longitude, if we're dealing with transverse waves, it is important that both of these waves should be polarized in the same plane. I mean, if they are polarized, they should be placed polarized in the same plane. But if they are unpolarized, no big deal. Unpolarized waves will simply cross into each other, no big deal. But if they are polarized, they must be same plane polarized. Now, this idea of what does it mean same plane polarized? I mean, what is it polarization? I haven't discussed it yet. I'm going to discuss about the polarization part in the polarization hearing. So don't bother, don't worry about that factor for the time being. When I'll discuss that, this part of the definition will become very clear to you. So I'll explain this for you. But I was just saying this in this part because you have to have in your head that there are three key components for the stationary wave or standing wave to be created. One is that the two waves should be of same type. They should physically merge with each other at a given time in the same physical space, and if they are transverse waves and if they are both polarized, they must be polarized in the same plane. Otherwise, they will not produce stationary wave. So bottom line difference, if I try to give a small the very key difference between progressive wave and stationary wave. Progressive wave is one wave which is carrying energy from one place to another place in a very simple way. That the type of wave that we have learned so far in our O levels. Stationary wave or standing wave is the type of wave where we have two identical or similar type of waves coming onto coming from opposite direction and meeting each other at a given time in the same physical space, and the net energy flow of the combination of the waves is zero. That's something that we're calling standing waves or stationary waves. You have to understand one thing: the energy is actually flowing through a stationary wave, but the net energy flow is zero. It's something that I can bring about for the idea for the what happens to the chemical reaction for the equilibrium state of উপমুখী বিক্রিয়া English কি জানো? For a reversible reaction. What happens at the equilibrium state of a reversible reaction? The reaction doesn't stop. It just has equal rate of reaction both in forward and backward direction, right?
Yes.
Okay.
So sir, it's like the energy is coming and at the same time it's going back.
Exactly. So
like
energy transfer হচ্ছে না, ব্যাপারটা এরকম। energy transfer হচ্ছে, but it is equal amount on both sides. That's why there is no net energy flow. That's the reason we use the term standing wave or stationary wave. And the term standing wave has also another physical significance, which I'm going to show you whenever I'll show you some animation and some video from the YouTube as well. I'll do that after 6 minutes. I'll take a small break. Be right back. Because if you have to take a break, take a break.
আচ্ছা স্যার, একটা কথা বলি। মেকানিক্যাল ওয়েভস আপনার মিডিয়াম লাগে নাকি, আর ইলেকট্রোম্যাগনেটিক ওয়েভসে কোনো মিডিয়াম লাগে না নাকি?
হ্যাঁ।
আচ্ছা স্যার।
The next point that we have is let me just explain the idea of progressive wave and this thing. Actually, I have this thing over here, standing wave formation. So let's just pause it. Okay, let's have a look. I'm erasing all of I'm showing you one progressive wave over here. So have a look. This is a progressive wave. This is a blue wave. Here the horizontal axis is drawn in radian. That's why we have 1, 2, 3, 4, 5, 6. So this one is going to the left, and within the same physical space, let's say we have another red wave that is going to the right. If these both waves are going to meet onto each other, they are simply going to merge with each other in terms of their displacement, individual displacement. So if we pause it, let's say if I pause it right over here, where I can so whenever this type of situation will happen, when the two waves will merge with each other with perfectly synchronization, the amplitudes are going to be added in all positions. In that case, the resultant wave is going to look like this, the violet wave that you see. This is what we call constitutive superposition or constitutive interference. Interference and superposition are pretty much similar word, interference or superposition. So this is what we call constitutive superposition. And in another case, let's say if we have the two waves meet at perfectly opposite phase to each other, for example, a situation like this, where you can see that the red wave is trying to push the medium particles upwards for this loop, blue is trying to push them downwards, opposite over here compared to this one. So here all the both the individual waves are trying to push the medium particles in opposite direction. In the case, the resultant wave is going to be zero. I don't have it perfectly zero because I could not make it perfectly zero. And you can see that the purple wave is basically the sum of the displacement of both the blue and the red waves. Do you understand this? So this is basically the idea of superposition. The blue wave is moving from left to right, and sorry, the blue wave is moving from right to left, and the red wave is moving from left to right. So these two waves are individual progressive waves, and their sum is producing the stationary wave, which in this case is the violet one. Why is this going?
Sir,
Yes.
stationary করলে 0 জুল এনার্জি ট্রান্সফার হবে না?
The net energy transfer will be zero.
তাহলে এই রেজাল্টেন্টটার যে অ্যামপ্লিটিউড এত বেশি?
Well, amplitude বেশি হওয়ার কারণ হচ্ছে the two waves are superposing onto each other to give us a resultant view of the total medium behavior. So the medium particles are going to be moving like the way the violet wave. We're not going to see the individual effect of the red or the blue wave. So the two progressive waves are going to work on the medium particles, but the total behavior of the medium particles are going to be seen as the sum of the two individual progressive waves. So distortion will be always added together to get the whole thing. So you can see over here, if I just try to so this is a case of destructive superposition, perfectly destructive, and this is the case of mixture of constitutive and mixture of destructive, and this is the case of perfectly constitutive. Oh, I just missed out.
সুপারপজিশন হচ্ছে যখন পার্টিকেলরা মুভ করবে না।
Well, কিছু particle সবসময় মুভ করবে, কিছু particle কখনোই মুভ করবে না. For example, these particles that you can see at the cross points of these two waves, for example, right over here, right over here, right over here, you can see that for the structure of the violet wave, these particles are never moving. Have a look. That this particle is always
Sir,
stationary.
it's just sir, it's just for a single frame of time, sir.
No, this is for a continuous process. Let me show you a video for this, which might be actually easier for you to grasp. Let me just show you just a second. think the first one was also good. This one is very good. Okay, what you need to understand that in this case, one of the ways, one of the effective ways by which we can actually make the standing wave possible is by simply making the last end fixed. So if we keep the last end as fixed, we're gonna have one wave traveling forward, and that same wave is going to reflect back. For example, let me just show you this for one pulse. Have a look. If we have, let's say this is a string that is perfectly tightened over within this part. We have this end can be oscillated, this end is perfectly fixed. So if I just produce one pulse, so this is a pulse, this is what I call one pulse. You'll see that this pulse is going by, the energy is going to fall over here, and then they're going to be reflected back, and eventually this and this is coming back. So this is, so what I'm trying to show you is that the wave, if there is no energy loss, considering there is no energy loss for the sake of simplicity, the wave can actually travel back and forth continuously. So if I, other than having a simple pulse, let's say if I give it a manual oscillation, let's say like that, you'll see that this wave will go over here and it will become flipped. In this case, you can see that on the front you have the crest, and now as it becomes flipped, on the left it has the so the wave has become reversed. So this is what we call a single pulse of a wave. Because there is a fixed end over here, the wave can reflect back. Now, if we allow this thing to happen continuously, what's going to happen? These incoming waves are going to get reflected over here, and we're going to have a production of a stationary wave. Now we can see the stationary wave is getting produced, because as the reflected waves are coming back, they are merging on the produced waves, and we have a situation of stationary wave. You can see that some of the particles are always moving, some of the particles are never moving. It's slowly becoming bigger and bigger and bigger, but this is not
মানে কোনো এনার্জি ট্রান্সফার হচ্ছে না, এই জিনিসটা যে হচ্ছে
exactly.
অ্যামেজিং।
Wait, let me try and adjust this thing for a better. View. Hold up. Yeah. So now, দাঁড়াও। সো এটা হচ্ছে সিচুয়েশন। এই পয়েন্টটা আমাদের পারফেক্টলি ফিক্স থাকার জন্য আমাদের এই পয়েন্ট থেকে ওয়েভগুলো রিফ্লেক্ট হয়ে ব্যাক করতেছে। সো দ্যাট ওয়ে উই হ্যাভ the production of two identical waves going in opposite direction. So this is producing a progressive wave from left to right. The reflection is producing a wave from right to left, and these two superposing onto each other is giving us a scenario where some particles of the medium are moving at a very high amplitude, some particles of the medium are moving at a very low amplitude. Why did it come to us? এটা এটা এই জিনিসটা পারফেক্টলি করতে না পারার কারণ হচ্ছে আমি এই জিনিসটা পারফেক্টলি অ্যাডজাস্ট করতে পারি না। এটা আমি জিনিসটা অ্যাডজাস্ট করতেছি।
স্যার
Just wait a little bit. I'm trying to sync up two of these green particles so that we can actually have a better understanding of this whole thing.
Sir, will it work if you switch from oscillate to manual?
I think now it's good. Have a look at these two particles. At the crest both. আচ্ছা আমাদের ওয়েভলেন্থ একটু বড় লাগবে, তাই ফ্রিকোয়েন্সি একটু কমানো লাগবে।
স্যার বুঝতেছি না স্যার কি হচ্ছে স্যার এখানে।
আমি একটা জিনিস অ্যাডজাস্ট করার চেষ্টা করতেছি।
ওকে স্যার।
For it. I thought I got it. আচ্ছা এটা ফিক্স করা আমার অনেক ট্রায়াল এন্ড এরর করা লাগবে অথবা অ্যাকচুয়ালি ম্যাথমেটিক্স করে বাই করতে হবে। আমি তোমাদেরকে ভিডিওটা দেখাই, তাহলে এই জিনিসটা বোঝা যাবে। এই ভিডিওটা দেখো সবাই।
So what we have here is a frequency generator. It's connected to.
This is actually a frequency generator which is going to cause this electromagnet to go up and down at a variable frequency. So this end is actually tied with a string and the other end is tied with a fixed end. As this thing is going to go up and down, this is going to produce a progressive wave which is going to go from left to right, which is going to reflect of the stuck end on the right side and it's going to reflect it back. Together they're going to produce a stationary wave. So here too what this teacher has to say, and this will start to make sense. I'll help you understand better, but I put a video time at the
What's called a wave driver. It's just a speaker. It's going to pump up and down at whatever frequency I set this guy to. When this guy pumps up and down, well, he sends a wave. He sends a wave down to this end, the wave reflects, comes back. Now, if I set it to just any old frequency, let me just turn this on. Well, yeah, let's go a little higher. So it's sending waves back and forth, but these waves are out of sync, if you like. They're not exhibiting consistently constructive or destructive interference at any one point. But if I set it here, for example, I have what's called a standing wave. That is, the wave that's sent down and reflects constructively interferes with the next wave that comes down right at this point. Now the waves that come down and reflect destructively interfere with the incoming waves right here, and that's called a node. I can touch it and it still is working. So the node is not moving. Here it's moving up and down, and here it's moving up and down. And we'll see that in a second with the high-speed camera. So here we have what's called the second harmonic. It's the second possibility for a standing wave for a string that's held at both ends. Because notice this is a node, and the middle's a node. So we have three nodes for this wave. Now, like I said, second harmonic, well, what's the first one? The first one will be half this number, so 8.5. And there we go. basically the scenario of a jump rope. Now, I can find any of the other all of the other harmonics are multiples of this number. So we just saw that 2 times this number was the second harmonic, or the second possibility. Well, if I go 3 times this number, I should get the third harmonic. Well, 3 times 8.5, I guess that was around 25.5. And there we go. So that's the third harmonic. How many wavelengths is this? Well, it's 1 and a half. 1 1/2 wavelengths. And it's easier to see in high speed. So check out this shot with the high speed camera and verify for yourself that it is 1 1/2 wavelengths. So again, third harmonic, 1 1/2 wavelengths. Well, let's go to the sixth harmonic. The sixth harmonic will just be double this frequency. So we go up to 50. And there we go. That's the sixth harmonic. Beautiful. And it's 6 times the fundamental frequency, which we measured in the beginning to be 8.5 hertz. So check this guy out. We have 1, 2, 3 wavelengths. And in the next video, the explanation video, we'll go through the calculations and the derivations.
Okay, this is a very nice demonstration for the stationary wave part. I'm definitely gonna create this teacher in my description. I'm looking forward to it. Might have to subscribe him. Yes, very nice animation. Now, what is important for you to understand? I mean, what I'm trying to explain to you within this part, standing wave formation. That here's the deal. If I don't show you the purple wave or the violet wave, this is only the 2 waves, one progressive waves going one into another way. So the blue one is going from right to left, the red one is going from left to right. So these are 2 identical waves going in opposite direction, one with respect to another one, and they are perfectly meeting onto each other. Now, if we try to find out that what's going to happen to the medium because of the combined effect of both of these waves, this is going to be basically the sum of these two amplitudes. Have a look over at this equation. Have a look. This is a sin fx plus p. This is the blue one, and this is the red one, a sin fx minus p. These are the variables given, so that we can change the value of these variables and change the shape of this wave. And then the resultant wave is basically the sum of these 2 things. And you have to understand these things are the equation for displacement variables. So they are displacement variables means that they can be positive or negative. So what is happening here? Have a look. Whenever the 2 waves perfectly merge with each other, for example, a situation like cannot get this over here, maybe a situation over here. So for a situation like this, here both the waves, red and blue, they are trying to push the medium particles in the same direction. So overall, through all the wave, their push direction is same. For this part of the wave, both the blue and the red are trying to push the medium particles upwards. So we are adding up the amplitude or displacement of the individual wave particles over here, and we're getting this maximum amplitude over here, and the same thing over here as well. In this instance, for this position of the medium, we have constructive interference in over the entire medium. Constructive interference means that both the waves are adding up towards each other's effect. They are not opposing each other in any way. Whereas if we start to play this, let's say if I start to go for it, now you'll see that there are certain regions in this medium where the waves are not perfectly cooperating with each other. Some places are cooperating, some places are not cooperating. So what do I mean by that? Let me just take a snapshot of this thing so that I can make sense with you in the whiteboard. Let's say I'm gonna copy this part up.
Sir,
Yes.
যখন সবগুলা পার্টিকেলস ওই যে মিন পজিশনে থাকে তখন কি এনার্জি ট্রান্সফার ম্যাক্সিমাম হয় নাকি তখনও 0 জুলস?
The energy transfer, net energy transfer at any point of time is 0.
দুইটা যদি যে কোনো সময় যদি ওভারল্যাপও করে বা কাছাকাছি থাকে, দুইটা ওয়েভের ওভারঅল এনার্জি ট্রান্সফার সবসময় 0 জুলস হবে।
Yes. You can
Given
say
that
when the medium particles actually come exactly at the mean position, they are at mean position at that instance, but their velocities are not zero. You have to understand the particles which are going downwards, they're at a pretty high speed, right? So
this
the whole medium is not void of energy. There is an amount of energy, but the energy transfer is happening equal amount by both opposite direction.
এটা কি এভাবে বলা যায় ওইটা ওইদিকে চার্জ জুল ট্রান্সফার করতে যাচ্ছে, ওইটা আরেকদিকে চার্জ জুল ট্রান্সফার করে যাচ্ছে, এভাবে 0 জুল ট্রান্সফার হয়েছে।
Yep, you can say that, but you need to use that idea of within a fixed amount of time, because as
টাইম সেম হবে আর দুইটার সোর্সেস সেম রাখতে হবে while the waves are happening.
exactly, that's the basic reason we call it a standing wave, but that can be slightly variable if the amplitudes of the two sources are slightly different, which I'm going to show you, don't worry. আচ্ছা, এখানে আমি জিনিসটা দেখাচ্ছি, সেটা খেয়াল করো। Whenever we have a situation like this, we have a mixture of constructive and destructive position on the medium. Have a look. I'm going to divide up this graph. I'm going to divide up this graph into multiple vertical sections to make sense with you. In particular, খেয়াল করো, let's say I'm starting from here. Okay, have a look for this part. This blue part of the wave is altogether above the y-axis on the positive y-axis side. This red part is also on the positive y-axis side. Okay? So if I try to draw a vertical segment over here, here, for this much part, both the red and the blue waves are trying to push the medium particles upward direction. So the resultant dispersion is found by the sum of these two. This part is a constructive interference segment. Now let's have a look for what is happening on the opposite side. So if I try to divide up this medium through this line, if you're wondering how am I choosing this line positions, it's going to make sense to you just in a while. Have a look. Just keep watching. If it doesn't make sense, I'll make sense to you. Don't worry. I'm sectioning the whole graph by individual vertical segments. Have a look. For this much part, the two waves are on the same side, but have a look for this much segment. Have a look for this segment. Have a look. What is happening here? For this much segment, we use a different color, maybe green. The blue is trying to push the medium particles down, but the red is trying to push the medium particles up. This is basically where we have opposite type of pushing on the medium particles, and that's where the two waves compensate each other's effect, or they try to work in opposite direction of each other, which we call the destructive interference. So here we are going to have destructive interference. So what you're seeing is that this, the displacement of blue wave added with the displacement of the red wave is giving us the rise to the purple wave. So over here we get a perfect zero because this is the position where the displacement of the red wave is exactly equal to the displacement of the blue wave. So together you are getting zero. So this is the part where we are having destructive interference because the two individual progressive waves are working against each other. Once again, if we go look out for this part segment of the wave, here both the red wave and the blue wave are trying to push the medium particles downwards because their individual positions are down, so they're both pushing them down. So this part here, they're helping each other out, we get a larger displacement. So this is the constructive part. Once again, this much would be destructive because the blue part is trying to oppose the red part. And then we have a constructive. Then within this segment, we're going to have a destructive. In this segment, we're going to have a constructive, and so on and so forth. This goes on. Do you understand what I'm trying to mean over here? When the individual graph segments of the two progressive waves are on the same side of the x-axis, they are going to add up to each other. For example, have a look. Let's say for this part, the blue wave for all of these blue wave curve coordinates, they have plus x displacement, right? And all of these red points, they also have plus x displacement. So if you add these two, they are going to all add up together. There is not going to be any subtraction. There's going to be actual addition. So that's why we call this part to be constant interference, because they are both adding up towards each other's effect. Likewise, if we consider this segment over here, for example, up to for this much part, Here you can see that the red wave is negative, the blue wave is also negative. So their combined effect on the medium is gonna be working in the same direction as well. Both of the individual waves, red and blue, they are trying to push the medium particles in the same direction, downwards in this case, but they are adding up towards each other's effect, not working against each other, rather working with each other. That's it.
Ji sir.
So the push direction is same. That's what's making this part another constitutive interference scenario. Whereas for the in between part, the let me use maybe the rainbow color. So the red wave was above the x-axis. This was a positive part for the red wave. So let's say this is the plus displacement. So the red wave, a red progressive wave is trying to push these medium particles in the upward directions, whereas the blue wave is trying to push the medium particles in the downward direction. Here they are trying to work in opposite side. So that's where we have distributive interference, because they are trying to push in opposite direction. So the resultant behavior is going to be smaller than individuals, each one's individual effect. So that's why the displacement over here is actually becoming sharply decreasing. Here we have 0, where the individual displacements are practically equal to each other. And then once again, we have this point over here. So we are having, for this scenario, we're having a mixture of constitutive, destructive simultaneously across the whole plane. And this is going to keep on happening if we try to look at the scenario over here. Have a look. If I try to move this, have a look. Whenever the two waves are perfectly overlapping onto each other, somewhat of this type, we have constitutive interference all over. And then we are going to have a mixture of constitutive and destructive. And there will come a certain point when the two waves will perfectly oppose each other's effect. I cannot make it 0 perfectly. Can I make it 0?
Waves গুলো oppose করবে নাকি particles গুলো?
The waves are going to push in opposite direction on the medium particles. Particles are going to be affected by both of the waves individually, but they're going to show only one behavior, pretty much like the way of force. Let's say you have an object. If you try to push an object by two different forces in two opposite direction, the particle is not going to give you two individually different acceleration. Forming up from the resultant force that you get as the combined effect of both the forces, you're going to get one resultant force and one resultant acceleration, right?
Yes, sir.
That's precisely what these particles are going to do. So I cannot make it perfectly at 0. Why is that? Well, if I play it in slow motion.
Sir, আমাদের এক্সাম যেটা হয়েছিল স্যার, ওইটার কারেকশন ক্লাসটা নেবেন তাই না স্যার?
হ্যাঁ। Somewhere over here, for a situation like this, you need to understand that in this case, this is the case of a perfectly destructive interference all over the medium. Here, the blue waves and the red waves, they are trying to push the medium particles all in opposite direction. The system or the medium still have energy. It does have a lot of energy, but because of this thing, all the particles apparently are on the same position. So this is the part that I want you to understand. Whenever this in the session, if in this demo, you can see. If I try to go over
Only 2 times this number was the.
You can see that AJ. What you can see over here, that this end is almost stationary. This part is also stationary. In the middle, we have also a stationary part, but these two parts are moving up and down at a very high amplitude. Do you see that? I mean, this point is almost not moving. Now, the question is why this middle point is not moving at all? Because there exists certain points within the stationary formation where some points always experience destructive interference. Have a look. Consider this point, for example. So let me just play this. Try to observe for this point what is happening for this exact point. Have a concentrate on over here. So let me zoom on into this one. Try to have a look at this point. You'll see that currently it has equal amount of red and blue in the opposite direction. If I allow it to move further, that difference is becoming smaller. I mean, the amount is becoming smaller, but the difference is remaining similar. So this point is still pretty much at the equilibrium position. So you see, this is not moving. This neighbor on the left side, these particles are moving up, these particles are moving down, but This point on its own is pretty much at the same position. If I allow it to move further, there comes a point of perfect match, but it just so happens at this instance of time, both the individual red and the blue waves, individual displacement at this location is 0. So 0 plus 0 still gives you 0. And as they separate out, once again, you start to have the other way of displacement. Now the red is giving you positive displacement, the blue is giving you negative displacement, but the sum of these two numbers is always remaining 0. So what is happening for this point over here? This point is always experiencing destructive interference. Do you see that? The two waves, blue and red, are always on opposite side of this point, of this location, no matter at what time instant you observe. So as a result, the total amplitude of this particle will be 0 because you are having no amount of displacement remaining on this part on this location, no matter what time that you consider. So this particle is always going to remain stationary perfectly. These are the points which remains perfectly stationary. For example, we have one over at 0, we have one over here, we have one over here, we have one over here. These stationary points, for example, if I just erase this red and blue, okay, you should be able to see it more clearly. Have a look. Some particles are always stationary. These particles are not moving. So if this was a rope, we would see this rope moving up and down in a fashion as if these points are not moving at all. Whereas these points, other points are actually moving. So the points which are never moving, these are the points that we're calling nodes. And the points which are having the maximum amplitude, try to understand. How are we defining them? The points which are never moving, they are defined as nodes. And the points which have the maximum amplitude, they are defined as antinodes. In this case, that antinode is this point. Let's say this location over here. So exactly at the halfway point between two nodes, you have an antinode. You have to understand that all of these particles, other than the node positions, are moving. But some points have more amplitude, some points have less amplitude. The location where you have the maximum amplitude, that's your antinode. You cannot say that particles which have no amplitude are nodes, particles which have amplitude are antinodes. That would be wrong. Because apart from the node positions, all the other particles have some amplitude. The particles which have the maximum amplitude for a standing wave, those are defined as the antinode particles, and those locations are defined as the antinode locations. Do I make sense, Pulavan?
স্যার
No,
ওই
sir.
যে স্যার ওই অ্যান্টিনোড আর যেটা বুঝছি স্যার, বাট ওই যে স্যার ডিস্ট্রাকটিভ ইন্টারফিয়ারেন্সটা কি ওই যে ওই জায়গাগুলোতে হয় যেগুলোতে পার্টিকেল গুলো মুভ করে না?
না, destructive interference আমাদের throughout the wave এর মধ্যে continuously constructive and destructive interference এর মধ্যে flip হতে থাকে. So at some instances you can have really full constructive interference, for example, for a situation, for a time instance where the two waves perfectly overlap onto each other, for example, a situation like this. Here you have constructive interference all over the wave. And then for some instances you can have destructive interference all over the wave whenever you have the whole medium coming to flat. So you are gonna have constructive and destructive interference on the medium continuously. For example, a situation like that, it's supposed to be perfectly flat. I couldn't pause it at the perfect moment. But what is happening that the positions where the nodes are, those positions are always experiencing destructive. But all the other positions are sometimes experiencing constructive, sometimes experiencing destructive.
স্যার
Sir, destructive interference মানে exactly মানেটা কি স্যার? Exactly, sir.
Destructive interference মানেটা হচ্ছে when the two individual progressive waves which are overlapping into each other, which are interfering with each other, they have opposite displacement with respect to each other. For example, one has a positive displacement for that location, the other one has a negative displacement. So the two individual waves are trying to push the medium particles in two opposite sides. That's the scenario that we call destructive interference. Basically, let's say you have an object that you are trying to push by two opposing forces in opposite direction. So if those two forces are not equal, you're going to have a little bit of movement. If those two forces are perfectly equal, no matter how big those forces are, your resultant sum of forces is going to be still 0. So if the individual waves are trying to push the medium particles in the opposite direction, those regions are what we call destructive interference.
Meaning, sir, the location where the waves are trying to push each other, I mean, meet each other and unable to push each other.
the waves are not pushing each other. The waves are trying to push the medium particle in opposite direction. That's why we have the distributive interference.
Oh, sir, that means these. Just a moment, sir.
Sure,
So,
sure.
sir,
Bolo.
sir, these locations where particles are not moving, these are the destructive interference, because one wave is trying to drag it down, while the other one is trying to drag it up, and as a result, it's just staying in its stationary point. I mean, neutral point.
Precisely, but there is one thing, additional thing that needs to be added to your description. Your description is perfectly all right. Is that these particles are experiencing destructive interference all over the time. I mean, not even a single instance of time, they're experiencing constructive interference. They're always experiencing perfectly destructive, which means these node positions are always having red equal amount of up, in which case the blue would be equal amount down, or the blue is equal amount up and the red will be equal amount down. So these node points are always experiencing perfectly destructive interference. Always. That's why they are never moving. I mean, there are some will always be, let me just write it over here, plus x. Why can't I write this? So for the destructive interference points, or for the node points, the total distribution is always plus minus x. No matter which wave you choose, you will always end up zero. The individual value of these x's can be different. The individual value of these x's can be different, but you will always have it. The sum would always be zero. Do you understand why the individual value of the x can be different?
Because they're coming from different opposite sources.
Exactly, they're coming from opposite direction. For example, if you try to observe over here at this position, at this instant where I've paused over here, let's say right over here, no, not this point, for the 0 point, right over here at this exit position, both of their individual displacements are maximum, but the sum is 0. If I allow it by a little bit, you have a little bit decrease in the value of blue. You also have a little bit of decrease in the value of red, but the individual amounts are exactly equal. So once again, the sum of the two individual displacement is still very much 0. If I allow it to move it a bit more further, same thing. The red is slowly becoming less. The blue is becoming less. The red is also becoming less. But the sum of these two individual displacement is still remaining 0. So which means, what I'm trying to mean is that you can have different value of the individual displacement for the progressive waves, because the waves are crossing each other with respect to time, but the sum at the node positions will always be 0, which means the node positions will always experience perfectly destructive interference.
So, sir, can we also say that in the destructive interference, the energy of the wave is being lost completely?
I wouldn't say the energy of the wave is lost, because whenever we say lost, it actually has to mean that it has to be converted into some other form, because energy is considered to be indestructible. We can say that within this point, the medium particle will be seen not to oscillate, although it is continuously transferring energy. The medium particle would be seen not to oscillate, but it is responsible to transfer energy. Now you might wonder that how is it even possible that a non-oscillating particle transfers energy? Well, this can happen. How can I make an example of this?
Sir, is it like transferring forward and backward at the same time somehow?
Exactly.
Like conducting?
Some sort of that. Yes, you can have a analogy like that. Yeah, that perfectly is parallel with the idea. Hasan, ki bolchila?
স্যার মাথা ঘুরে স্যার, অনেকক্ষণ ধরে করতেছি তো স্যার, অনেক আজব লাগতেছে স্যার।
আচ্ছা ঠিক আছে, সমস্যা নাই, আমি তোমাদেরকে একটা গ্রাফ করে দেখাই।
স্যার ছুটি কবে হবে?
কিসের ছুটি?
না, আমার ক্লাস শেষ।
ও আচ্ছা, এটা তো ক্লাস টেস্টের কোশ্চেন। আচ্ছা, আমি একটা গ্রাফ দেখাই, তোমাদের ক্লাস শেষ করে দিচ্ছি। জাস্ট আ সেকেন্ড।
স্যার এই বুকলেট থেকে স্যার।
বুকলেট থেকে দেখায়, সমস্যা কি?
Sir, are destructive interferences and nodes are the same things?
একটু দাঁড়াও।
Oh,
হাই হাই, কই গেল?
sir, can you tell me the definition of the term superposition exactly?
বলতেছি, দাঁড়াও। I cannot find the question that I'm looking for. আচ্ছা, আমি কোশ্চেনটা বের করে রাখবো। কোশ্চেন আমি তোমাদেরকে টিউসডে দেখাবো, সমস্যা নেই। ওয়েভস এর বেসিক কি কনসেপ্ট অফ দ্য ড্রয়িং ইজ ভেরি সিম্পল। এটা তোমাদের কাছে কঠিন লাগার কারণ হচ্ছে যে তোমরা গ্রাফের এই লেভেলের ম্যানিপুলেশন এখন পর্যন্ত ফিজিক্স অ্যাটলিস্ট দেখো নাই। So you have some graphs given and you have to do some calculation from the graphs. You haven't seen it yet. So introducing this depth level of graph manipulation is new for you. The concept of constitutive and distributive superposition is very simple. Try to understand the basic idea. When two individual progressive waves are trying to push the medium particle in the same direction, which in graph appear to be on the same side of the x-axis, that part represents a constitutive interference. They are both pushing the medium particle in the same side, and vice versa. আমি বাকিটুকু বলতেছি না, ভাইস ভার্সা বুঝতে দেখো, তোমরা রিভার্স করে নিজে মাথায় বুঝতে পারো। বুঝছো কি বলছি?
Yes, sir.
থ্যাংক ইউ ভেরি মাচ।
Are the superposition a definition, sir?
আচ্ছা, আমি দেখাচ্ছি, দাও।